Welcome to The Explainer. Today, we're jumping into a huge topic in software engineering, the solid design principles. You know, if you've ever fixed one tiny bug only to watch 10 new ones pop up out of nowhere, well then this is definitely for you. We're going to talk about how to bring some much-needed order to that beautiful chaos we call code. So let's start with this question, because we've all been there, right? You find a small bug. It seems like a simple fix, maybe one line of code. You push the change, and then everything breaks in places you didn't even touch. It's super frustrating, and it's usually a symptom of a much deeper problem with the software's design. And this problem? It gets so much worse when we start talking about software at scale. What starts as a simple, elegant little project can, over time, grow into this massive, complicated beast that feels almost impossible to manage. Let's just paint a picture here. We're talking about code bases with millions of lines of code. You've got hundreds of different engineers all working on it at the same time. Things are changing constantly. And without a solid design philosophy, the whole thing becomes incredibly fragile. Bugs start piling up, and actually shipping new features, that slows to a crawl. So the real challenge then is this. We have to design software that can actually survive change. The whole point is to build systems that can grow and evolve without just completely collapsing under their own weight. And that's where this design philosophy called SOLID comes in. Think of it as a blueprint, a set of guidelines for building software that's robust, easy to maintain, and ready to scale. So what is it really? At its heart, SOLID is a set of 5 design principles. I love this idea of it being a design filter. Before you even write a line of code, you run your ideas through this filter. It helps you catch design problems early and make sure the final product is clean and built to last. So, what are these 5 principles? Well, the acronym SOLID makes it easy to remember. We've got single responsibility, open/closed, Liskov substitution, interface segregation, and finally, dependency inversion. Let's break down what each of these actually means. All right, let's get into the nitty-gritty. We're going to dive deep into each one of these principles, starting, of course, with the S in SOLID. Okay, the single responsibility principle. This one's probably the easiest to grasp. Think about it like this. You want every employee at a company to have one very specific job, right? You wouldn't ask your marketing manager to go and rewire the server room. It's exact same logic for our code. And this slide lays it out perfectly. On the left, you've got this one order service class that does everything. It places orders, calculates tax, saves to the database, sends emails. It's a mess. A tiny change to the tax rules could accidentally break the code that sends emails. But on the right, in the SOLID design, every task gets its own class. So if you change the tax calculator, you know you're only affecting tax calculations. It contains the blast radius of your change, which is a huge deal. And here's the official definition. It's so simple and powerful. A class should have only one reason to change. If you find yourself changing a class for lots of different unrelated reasons, that is a massive red flag that it's doing way too much. Next up, we've got O for the open/close principle. This one is all about being able to add new features without having to change existing code that already works. I know, it sounds a bit like magic, but really, it's just smart design. Take a look at the problem on the left. You've got this big, ugly if-else block for payment types. What happens when you want to add a new one? You have to go in and mess with that code, which is always risky. On the right, though, we use an interface. So to add a new payment method, we just create a new class. The original working code is left completely untouched. This is the key idea right here. Our code should be open for extension, meaning we can add new stuff, but closed for modification. This makes adding new features so much safer and, honestly, a lot faster. All right, now for L. And I know, the name is a mouthful. The Liskov substitution principle. But the idea behind it is actually pretty simple. It just means that a child class should always be able to step into its parent's shoes without causing any trouble. This is the classic example you always see. So on the left, you have a bird class, and it can fly. But then you create a penguin class that inherits from bird. Well, a penguin can't fly, so it breaks the contract of the parent class. The SOLID design on the right is much smarter. You have a general bird class and then a more specific flying bird class. The inheritance is logical, and you won't get any nasty surprises at runtime. At the end of the day, this principle is all about honoring a contract. A subclass has to be a perfect substitute for its parent. If it isn't, you're going to have problems. Moving on to I, the interface segregation principle. This one is all about avoiding what we call fat interfaces. You know, these giant interfaces that are bloated with a ton of methods that not every class is actually going to use. Just look at the problem here. A robot worker is being forced to have methods for eat and sleep. That makes no sense. The solid design on the right is so much cleaner. You just break that one big interface into smaller, more specific ones. The robot only needs the workable interface, and that's it. No extra baggage. And that's the core idea. Don't force your classes to take on methods and dependencies they don't actually need. Keep your interfaces small and focused. It just leads to cleaner, more logical code. And finally, we've arrived at D, the dependency inversion principle. This is a really powerful one for decoupling your code. It basically says that your high-level business logic shouldn't be directly tied to low-level details, like what kind of database you're using. This slide shows you exactly why this is so important. On the left, our order service is hard-coded to use a MySQL database. What if we want to switch to a different database next year? Well, we have to rewrite the order service. But on the right, the order service just depends on an abstract interface. We can plug in MySQL or any other database we want without ever touching the order service itself. And that's the big takeaway. By depending on abstractions or interfaces instead of concrete implementations, we create this awesome, flexible, plug-and-play architecture. It's so much easier to maintain and test down the line. Phew, we've covered all 5 principles. So you might be thinking, that sounds like a lot of work. What's the real payoff here? Well, it all boils down to 2 things that businesses care a lot about: scale and reliability. This table sums it up perfectly. When you apply Solid, different teams can work on different parts of the system without constantly breaking each other's code. That means you can move faster, you get fewer merge conflicts, you can add new features without having to do these massive, expensive rewrites. And maybe most importantly, you get fewer bugs in production, which means happier customers. But, and this is a really big but, it's super important to have a balanced perspective here. Solid principles are an incredibly powerful tool, but they are not some rigid law you have to follow in every single situation. There are absolutely trade-offs. You get this beautiful, clean, scalable architecture that's way easier to test. But the price you pay is often more classes and more files. It can feel like overkill if you're just building a small script or a quick prototype. The real skill is knowing when and where to apply these principles. And that really brings us to the final, most important point. Solid isn't about just following rules for the sake of it, or making things more complicated than they need to be. It is a set of practical guides with one clear purpose: to help us build software that is resilient, adaptable, and made to last. It's about writing code that survives change.